pain in the ass, right? Become a pain in the ass. Now you might argue, well, this is just as bad, right? But on a typewriter, I would just do this. I would use that caret key on the typewriter. So I could just keep typing. Anytime I want to do e to the x, I just do that. Just type. So I never have to stop, right? Subscripting is different. I have to stop typing and do this. So what humans decided is that instead of using that notation for that particular function, we're not going to use this notation. We're going to use this notation instead. Remember, this was what we called the natural exponential function. The natural exponential. So since this is the inverse of that, this is going to be called the natural log function. The natural log. And the way we write it is this. That is not in. That is ln. And it's French. French would not say natural. They would not say natural log. How would the French say this? How would the French say natural logarithm? They would say logarithm natural. That's the way the French would say. They would reverse it. So this is logarithm natural. Natural logarithm of x. So this right here and this mean exactly the same thing. But do you see if I'm typing this, I don't have to stop, right? Just keep going. Unfortunately, that is still used today, and students look at that and they completely forget that all it is this. What do you lose in this notation that you have here? You know well, you kind of know it's a log because of this, but what really is lost? The base. You don't know what the base is, do you? But you better know because that notation means that's the base. So students will often have this huge disconnect between this idea and this idea because the base has been lost, okay? So everyone just understand that when you see this, that really means this. So sometimes in this class you'll see me throw a little e here just to remind you of the loop, right? That there's really an e down there that gets looped around. Same with this one. Base 10, 10 fingers, we'd see this, we'd use it a lot, so we decided to use a different notation for this one. This one's a little more, I don't know. They just decided to write log x. That's it. So if you don't put a base, it's understood that the base is what? 10. So if you just write log x, the base is 10. You have to know that. And if you write ln x, then you mean the base is e. So this is the base 10, right? This is the base 10. Doesn't have a special name. It's just called the base 10 log, right? Base 10 log here. But this one is so great and so awesome, it gets its own name. It's called the natural log. All right, so what I'd like to do right now is I'd like to graph the natural log function. We're going to do it two different ways. I would like for us to sketch f of x equals ln x. Or inx. If you want to say it incorrectly, say inx. There are two ways to graph this right now. There's an easy way and a harder way. Not a hard way, but a harder way. So I'm going to do the harder way first, and then we're going to do the easy way. All right? The harder way is to understand that this is the inverse of what function? What is this the inverse of? Which exponential? E to the x, right? So do you agree that if I could come up with some points on e to the x, I could then just reverse them, and that would be points on this one? So that's one way I could do this. I could say, all right, instead of trying to graph that right away, I'm going to make a table off of x and e to the x. And e to the x, I can use my calculator, can't I? Just use my calculator. Did you all bring your calculators? I brought mine today. So I think we did this one last class, did we? Someone check in their notes. Did we plug in these numbers into the e? I don't know if we did. I don't think we did. Either way, let's do it. So everyone on their calculator should have an e button. And I want to make sure you can do this. If you do e to the negative 3, you should get approximately 0.0497, something like that. And then you go and you do e to the negative 2. And you get 0.1353, however many decimals you want to go. Then I do e to the negative 1. And I get 0.3678. I don't even care about rounding, right? It's not that big of a deal here. E to the 0, I know this one. 1. Okay, what about e to the 1? Well, e to the 1 is just e, isn't it? And I told you e is about 2.718. So this is going to be about 2.718. Then e squared, 7.389. And finally, e cubed, 20.085, something like that. There we go. So what I've done is, in order to graph the natural log function, what I did is I made a table for the natural exponential function, which is its inverse. And now the table for that one is just this table flipped over. That's all it is. So if I want this, here's x, here's natural log x, I know that when I plug in 0.0497, I get negative 3. When I plug in 0.1353, I get negative 2. When I plug in 0.3678, I get negative 1. When I plug in 1, I get 0. When I plug in 2.718, I get 1. 7.389, I get 2. And finally, 20.085, I get 3. Now I can graph this. And look at the way I graph this. Do you see I'm only drawing the right side? That's because I know that when I graph a log function, it only exists to the right of the y-axis, because the domain of this is that x has to be greater than 0. And then I plug these points in. 0.0497, negative 3. That means I move to the right just a little bit and go down 3. Let's put, what should I do? What's the biggest x value we're going to have on our chart? What's the biggest x value? 20, so I'm going to put 20 here. That means that's about 10. So I don't know, 1's about right there, somewhere around there. So if I plug in a very small x, little tiny x, and then come down 3. 1, 2, 3. Negative 3, put a dot there. And then I'm going to go 0.1353 to the right, which is a little more than that one. And I come down, I go negative 2. What's happening right here? What's actually happening with my graph over here? This is where I have that vertical asymptote, right? Goes like this. And then what about at 1? 0. We said that's going to be on every logarithmic function, right? 1, 0. There it is. And then 2.718. To the right, 2.718, here's 2, here's 3. I go up 1. At 7.3 something, I'm at 2. This is like 7 point something. And then at 20 point something, I'm up at 3. Okay, there it is. Y'all follow what I did there? Yeah. Okay, so I said this is kind of the harder way of doing it, because you have to do this and then you do flip them and then you graph them. The easier way is use the fact that your calculator has a button for natural log. And so what I do is, instead of doing this, I'm going to start over. I'm just going to use my calculator, and I'm going to go and make a table, x and natural log x, and just use my calculator. And remember that when I plug numbers in here, I can't plug in negatives, right? So I could plug in 1. So on your calculator, find your natural log key and do natural log of 1. Hey, what's natural log of 1? What's always going to be on every log function? 1, 0, right? So when you plug 1 into any log, you get 0. Okay, then plug in natural log 2. Everyone find their key? Yes? Everyone's found their key? What do you get when you plug in 2? 0.69? 3? Something like that? Plug in 3. 1.09. 4. We'll do maybe 1 or 2 more. 4. Man, this is not growing very fast, is it? 1.38. Let's do 10. Natural log of 10. 2.3. And then you'd graph these. Plot those points. Now, those points, if we were to put them over here, they would be 1, 0. At 2, you're at 0.69. At 3, you're at 1.09, something like that. At 4, you would be up a little further. At 10, you would be up here. It's hard to see those, but these points right here are the ones that we would have gotten off of this versus this one, which gave us those black points. So if we were drawing our graph, we would have to know it goes like this. We would have to know we have a vertical asymptote down here, and then we just continue it this way. Yes?
Wait, so is that because those two graphs look the same to me, so.
They do.
I mean, not the same, but like.
These look different?
Yeah.
It's because the inputs we've chosen are different. Here, we chose the inputs, right? 1, 2, 3, 4, 10. Here, did we choose these? No, those came off the table for the e to the x, right? Yeah. So we didn't get to choose these values, right? But what I'm trying to show you is that if you plot these points, they will lie on that same curve we just drew. They just won't be the same exact points. They'll be in different places, okay? So I don't know, you do whichever one you prefer. I think just the key on the calculator is nice, but you know, whatever. All right, there's natural log of x. Everyone have a basic idea of what it looks like? No? I'm going to get to this later, but I may as well now. Let me just ask you all a question. I want to know why this is true. Because I've said it's true, but why is this true? Maybe you can resolve this. Why is natural log of 1 equals 0? Why is log of 1 equals 0? Why is log base 3 of 1 equals 0? Why is log base 7 of 1 equals 0? Why is log base 5 of 1 equals 0? I told you that point lies on every graph, right? I told you, and I think we all believe it, right? But can you convince yourself why this is true? Yeah.
Is anything the power of 0 is?
Yeah, do the loop on any of those. Do the loop. Right, well, what's the base here? What's the base here? E, right? What's e to the 0? 1. Anything to the 0 is 1. Okay, what's the base here? 10. 10 to the 0 is 1. What's 3 to the 0? 1. What's 7 to the 0? 1. Right? So any log of 1 is 0. Any log of 1 is 0. All right, here's what I'd like us to do now. How are we doing on time?
If the base was 1, would this be a straight line?
If the base was 1, it would be a straight line, but then it would not be classified as an exponential or logarithmic function. Like, you know, with exponential was a to the x, but we said a couldn't be 1? It's exactly because if it was 1, it would just be a straight line, and then it doesn't really have growth or decay, right? So we just say, yeah, let's not consider that, all right? All right, so I'd like for us to do this. Sketch this. sketch it. Then after you sketch it, I want to know the domain and range. All right, this goes back to the idea of translations, shifting up, down, left, right, reflections, all that moving things, stretching things. We now have a new function in our toolbox. The new function that we have that we all need to know what it looks like is the function f of x equals natural log of x, which we just graphed, right? We all need to know now that that graph looks like this. And when you get to Cal 2, or Cal 1, you better know that too, and pre-Cal. This right here is the graph of the natural log of x. Basically, this is what it looks like, right? Have vertical asymptote here. Domain of this is 0 to infinity, range is negative infinity to infinity. That's the basic one. Now, we need to move it around and do things. So I'm going to start like an order of operations. I'm going to start on the inside. What does subtracting 3 do? Moves the graph which way? Right 3. So this right here moves the graph to the right 3. Okay, now I'm not going to do this yet. Now I'm going to come out here. Let's look at the negative first. What does the negative do? Flips it over which axis? Flips it over the x-axis. Okay, what does the 2 do? Stretches it which way? Vertical or horizontal? Vertical stretch. Vertical stretch. Lastly, plus 4. Up 4. Up 4, right? The number on the outside is always an up and down. The number on the inside with the x is always left and right, opposite of what you think. Y'all recall this, yes? Oh, yeah, that we did all this? Shifting? Okay. So what I'm going to do is I'm going to start with that graph. Okay, let's do it. Start with that graph. Here it is. I'm going to do it dotted because that's not going to be my final picture. There's my graph. And now, first thing I do is I move it to the right 3. So remember that point that was here? That was 1, 0. If I move that to the right 3, where does it go? 1, 2, 3, right here. That's now at 4, 0, isn't it? So now we've got this. Okay, be real careful here. There's something else I want you to pay attention to. The vertical asymptote used to be here. Now where is it? It used to be at x equals 0. Now where's that vertical asymptote? X is 3, because it moved to the right 3 as well. So if this is 1, 2, my drawing sucks. If this is 3, my vertical asymptote is now here. Right? This point moved to the right, this point moved to the right 3, and so did the vertical. It went with it as well. Now what? Let's go ahead and flip it, right, over the x-axis. So that means it's going to go like this. So now goes, everything that was negative now becomes positive. Right? And that vertical that used to be here is now up here. So it went right 3. It got flipped over the x-axis. Now what? Stretch it vertically. Now that's hard to do. It's hard to stretch things vertically, so you just kind of do your best. When I stretch it, what I'm going to do is every point that used to be here on the green, I'm just going to move that point up a little bit. Every point gets moved up. Actually scaled by 2, but I don't even care. This point will not move because it's, what's the y value of this point? What's the y coordinate? 0. And what's 2 times 0? 0. So that point doesn't move. It's anchored there. But these points get stretched, and these points get stretched down. So it'll look more like this now. Did the horizontal move? I'm sorry, did the vertical asymptote move there on that one? Not with the stretch. It's still here. One more thing. Up 4. And this will be my final picture, won't it?
Yep.
So up 4, I'm going to say this is 1, 2, 3, 4. Here's 4. See that point right there? Just move it up 4. Boom, there. And then it still goes up this way. We have that vertical. And it still goes down this way like that. That's a rough sketch. It's not perfect, right? What's the domain? To the right of 3. You can do that 2 different ways. You can look at your graph, right? Remember this was 3? It's just to the right of 3. Or you could get the domain by looking at the argument and doing the inequality. X minus 3 has to be bigger than 0, and then solving. Either way, the domain is 3 to infinity. And what about the range? Yeah, it's everything still. There it is. Okay, one last topic before we call it a day. What did we start class with today? What was the first thing I put on the board today? What was it? I gave you some equations to solve, right? I gave you some equations to solve. And you were trying to solve them, and we did pretty good, but then I gave you some that we couldn't solve, right? Those were called exponential equations because our variable was up in the exponent. We are now going to get into something called solving logarithmic equations. These are equations that involve a variable, x, that we're solving for, but we also have a logarithm involved. And today, just to end class, I'm going to give you some basic ones. Then they're going to get much harder, all right? So first, I'm just going to say log equations. Intro, so that you don't get too comfortable. All right, first example. Solve this equation. Log base 4 of x equals 2. All right, do you all see that that's an equation? Yes? Do you all see that you have a variable x in there? Do you see that the variable is inside of the logarithm? It's the argument of the logarithm. It's like this is the argument of that logarithm. Can you solve for x? How?
4 squared.
Do a loop, right? Do the loop. 4 to this power is this. 4 squared is x. What's 4 squared? 16. Done. That's pretty straightforward, yes? Okay. How about this? Log base 3 of x. Let's put a -2 in front of this. Yeah, equals -6. Is that an equation? Yes. Do you see a logarithm there? Yes. Is the x in the logarithm? Yes. Okay, how do we solve this? We're going to use a loop, right? But before you do the loop, you have to resolve the fact that there's a -2 in front here being multiplied. So what do you think? To get rid of this? Divide both sides by -2. Okay? So divide the left side by -2. Divide the right side by -2. And now you have the logarithm sitting by itself. And this side's 3, right? -6 over -2 is 3. And now you can use your loop. You cannot use your loop before that step, all right? It's at this step here. 3 to the 3 is x, so 3 cubed is x. So x is 27. Okay, how about this? How about log, let's go 5, log of x plus 3 minus 4. Okay, let's go 7? Yeah, let's go 7. Oh, shit. Hold on. Yeah, we should be okay. See, I'm building complexity to these. Just, I'm adding a little bit more each time. What do you think I'm gonna do first? Divide by 5, or what's the other thing I could maybe do? Add 4. What do you think I should do first? Add 4. Let's add 4. Okay, so we do that, we get 5 log x plus 3 equals 11. Now, divide by 5. Divide both sides by 5, you get log of x plus 3 equals, what's 11 divided by 5? 11 fifths, which is 2.2, I believe? 2.2?
2.2, yeah.
2.2. Now what? What do we do here? Once we got the log by itself, what do we do? Loop, right? What do we do here when the log was by itself? Loop. What do we do here? Loop. But loop with what? What's the base? No, what's the base of that log? 10. See, I got you, didn't I? That's the special one because we had typewriters, right? So this is a 10 down here. See, if you forget that, then what are you going to use for your loop? There's really a 10 there. So this is 10 raised to the 2.2 equals x plus 3. 10 to the 2.2, I'm going to need my calculator for, right? I'm going to have to use my calculator, and I'm going to take 10 and raise it to the 2.2. I'm trusting you know how to do that on your calculator and get 158.49 or so. 158.49. Is that our final answer? No, because we haven't solved for x, have we? Oh, do y'all understand why this, I kind of went over it real fast. It was 10 raised to this equals everything here, right? Whatever's here goes here. Okay, so here you just subtract 3, right? So 155.49. That's your x. I have 3 minutes, man. I really want to show you something, but I think this would be a good place for us to just call it a day. Yeah, no, sorry. Now, I just want to show you this one last one because it's here at the end of the section. Sorry, this will be fast. E to the 2x equals 5. Okay, that is not a logarithmic equation, is it? That is not a logarithmic equation. Do you all agree with that? That's not a logarithmic equation? And we don't know what it is because, we don't know the answer because what we're saying is e raised to the 2x. This is like what we started class with, right? We're trying to solve for x. The reason I can't solve this is because e and 5 are not the same base, right? So I can't figure out what this is. But now what I know, right, from today, is that I can rewrite this from exponential form to log form. What's the log form of that? Oh, sorry, the whole thing. Sorry, I meant the whole thing. What's the log form of that whole equation?
Log.
Log, what base? E, okay, equals, okay, 5 here and over here, 2x, right? However, what is really log base e? What is this for real? No. This is where humans were like, hey, log base e, I have to type that. That sucks. The French came in. This is actually just means natural log of 5, doesn't it? This means natural log of 5 equals 2x. Isn't that what that means? And do you have a calculator key that can figure out what natural log of 5 is? Yeah. So you figure out what natural log of 5 is real fast. I'm going to continue up here. You get 1.609 equals, that's this side, and the other side is 2x. And then just divide by 2. And you get 0.80, 0.804 something. Now, I will tell you, this appears at the end of the section. We can only do this right now, as of right now, we can only do this if this is e. Because when we do the logarithmic form, this will be log of e, or log base e, and that we have a key on our calculator for. If this was like 4 to the 2x, we can't do it yet. Next class we will, all right? So do what you can for your homework for this. I got through most of the section, not all of it, but I think you have enough to get going on the homework. Let's officially say we're going to have that test before Thanksgiving. That's what most of y'all wanted, right?
Yeah, 23rd.
Yes, please.
Which is the Wednesday before we will have our next test. I'll talk about that more next week. So it's not next week, right? It's the week after that. Wait, sorry, Tuesday. Did I say Wednesday?
Yeah.
Sorry, Tuesday.
Is it so? Because we have Thursday off, right?
Thursday's a holiday, yes. Okay. Excuse me.
On Tuesday.
Okay, let me see. Yeah, I haven't looked at these yet. Thank you. Wait, no, I think I did, but I'll